Okay. Hi, everyone. I'm just going to dive in probably. So this is joint work with Mr. Hugh Nguyen and Dr. Christian Wassler. Okay. As we all know that group contest from the IO literature has been, used to characterize a lot of different environments in order to analyze group behavior. We focus on two specific aspects of group contest here. First being heterogeneity. So we focus on between team heterogeneity. The idea here is that competing teams may differ in one dimension or more. So just as an example, some public or private organizations may have larger resource base, or they may have more number of employees. So the idea is that they may be able to incentivize effort better from their employees as compared to their competitors. In addition, we focus on the information conditions here. So teams may or may not have complete knowledge about their opponent. And just as another example, research labs may typically know who their main competitors are, but it is highly unlikely that they precisely know their talents or their team compositions. So here, Bhattacharya examines these types of heterogeneous contests, and she calls it even and uneven contests, where even contests are basically ones where competing teams are on equal footing in terms of these incentives, whereas, of course, uneven contests have more to do with heterogeneity between teams. So she finds that this heterogeneity does impact group level effort. So Malug and Yates show that theoretically incomplete information over these incentives does alter effort, and they show it in an individual contest setting, but we can easily adapt their framework to ours, because in our group contest, we assume that the team members are identical. Another stylized fact from the literature is that a lot of experimental studies record over expenditure of effort as compared to theory. Another implication of that is that the standard self-interest theory means that whenever there is a group size advantage or heterogeneity with respect to group size within these teams, the theory does not reflect any group size advantage, but empirically, there is a departure from that theory. So we do try to address that with our paper. So we really focused on this question of how incomplete information over incentives affects group effort in both even and uneven type contests. By doing so, we provide the first experimental evidence on incomplete information and its impacts. And we do so with respect to three sources. So these are the three main sources highlighted in the literature that could impact group effort. First is the effort cost, the price value, and the group size. There is a lot of contention with the group size, so we try to address that. Apart from the standard self-interest model, we also consider a within-group cooperation model, and we find that it does a good job or a better job in explaining the over-expenditure of effort and a theoretical group size advantage. So our model is really simple. There's a group G that consists of n identical players. So there is within team homogeneity here. And two groups compete for a common prize, V. So V is valued as a public good. It is worth V to each member within the team. Players exert independently and simultaneously exert effort X at a constant unit cost. And we assume that the player efforts within a team are perfect substitutes. So we can just add up individual efforts to obtain the group effort here. The contest success function, or the probability of winning, is a very simple one for the lottery contest. Basically, the probability of win is determined by the relative efforts of these competing teams. And because we focus on more of a discrete analysis here, groups can either be advantaged or disadvantaged. So they're either assigned the parameters of an advantaged group or a disadvantaged group. The first information condition that we look at is complete information. Here we assume that all parameter values with respect to these three sources are public knowledge for both the own group and opponent. So our objective function it's pretty easy, but here what I'm showing is the objective function for a cooperative model. So the difference between the two is that the standard self-interest theory assumes that each individual will maximize their own benefit from an additional unit of effort. But with our cooperative model, we assume that each individual within a team maximizes the group benefit, or they consider the expected marginal benefit to the group from that additional unit of effort. So mathematically, what that does is we can sum up over this objective function such that in that first term there, I'm so sorry, on that first term there, we get that n term, which represents the group size here. So the first term is really telling us the expected value from winning for the entire group, less the total cost to the group. Because there is no group size, like the group size does not play in the self-interest theory. Self-interest theory does predict no group size advantage, but the within group cooperation model helps us get there. The other information condition, which is the main, which is the focus of our paper, is the incomplete information. So here we assume that there's a probability R that the opponent will be an advantaged group. So basically, our contest success function is the one that gets affected by this probability. Just as an example here, what we are doing is we are considering, we are maximizing the expected benefit just as before, but given the expected value of opponent's efforts. So I know it sounds like a tongue twister, but basically what we are doing is with probability R, that contest success function, as a group G, I would best respond to an advantage group's efforts, which is why in the denominator, you see that XA term. Similarly, with 1 minus R, I would best respond to a disadvantaged group. So it becomes more of a probabilistic kind of a contest success function. We do provide a general result with our propositions overall, but for the experiment, we focus on the special case where either being an advantage group or a disadvantage group is equally likely. So we focus on R equals 1/2. These are the three main propositions from our model. The first one looks at uneven contest. So again, there is between team heterogeneity with respect to three sources here. We find that in such situations, incomplete information increases the contest level effort. With even contest, theory predicts incomplete information to decrease the effort. And with proposition 3, what we are really testing is, regardless of the contest type, what happens to the expected effort. So here, when R is less than 1/2, meaning when there is relatively, it is unlikely that you will face an advantage group, the expected contest level effort is higher in incomplete information. But when it's highly likely that you will face an advantage group, it turns to more of a discouragement effect, where incomplete information would reduce the effort as compared to complete information. Lastly, when R is 1/2, so this is the one that we employ with our experiment, we find that expected contest level effort is exactly equivalent under both conditions. So our design is pretty simple. We employ a 2x3 between subjects design. On the information dimension, we vary two conditions, basically complete and incomplete. Now the advantage dimension, we look at these three sources. So that gives us a total of 6 treatments. Now, one thing that I want to mention here is that competing groups in our experiment can only differ in one dimension at a time, but ideally the theory is pretty general, so it's possible to derive multiple, it's possible to have multiple differences here and derive predictions for those. We do employ a threefold advantage across all three sources just to maintain theoretical equivalence. So just as an example, if the cost of effort is 1 unit for the disadvantaged group, then it would be 1/3 for an advantaged group. Till now, we've completed 18 sessions with 324 students, and we're left with 2 more sessions for the group size treatments. So we're almost there, but our results are still on the preliminary sort of side. In the design, like I said, we focus on R equals 1/2. So we assume that there's a 50% probability of the group being either an advantaged or a disadvantaged group. And because this probability is independent for each group in each period, there is a mix of even and uneven contests in a particular session. We start with a risk elicitation task in stage 1, and then before moving on to the decision task, we make sure that the participants go through a small quiz to understand whether they can calculate the probability of winning and the expected payoff correctly. So on their decision screen, um, it looks something like that. Basically, under the incomplete information, they're given information on their own group, which is the left panel. So they know all these parameter values. For the opponent group, because it is the incomplete information treatment, for incomplete information cost treatment, basically, instead of actually knowing the value, they know that there's a 50% chance of the opponent being advantaged or disadvantaged. And of course, on the right side, they make their contribution decision. So when we compare these average group contributions with our point predictions from theory, here like I said, we focus on two theories, standard self-interest, which has been studied in the prior literature, and the cooperative Nash equilibrium. So the cooperative Nash equilibrium ideally would be much higher as compared to the self-interest, because it accounts for that group maximization behavior. So we can see that on average, the within group cooperation model does a better job of matching the data as compared to the standard self-interest model. And again, that's with respect to all the three sources. So moving to the results, we have five main hypotheses, but I'll show you maybe some interesting ones just to keep the time in check. We state all of our hypotheses as null, and the first three hypotheses are derived from our three main propositions. The entire analysis at the group level, so our dependent variable is the group level effort in all of these tables. With specification one, we are testing, or with hypothesis one, we are testing the impact of incomplete information in uneven contests. So again, these are contests with where there is between team heterogeneity. With specification one, we just test in a very simple way. We assume, so I'm sorry, we use the incomplete dummy, which is equal to 1 for all the incomplete information treatments according, so we just average across all sources, and we find that incomplete information does increase effort. So this by almost about 13 points, this is in the direction that theory predicts, both the self-interest and the cooperative model. With specification 2, we allow these incomplete information effects to vary across these three different sources. So value and group are indicators for the value and group treatments. So our baseline is really the cost treatment here. Now with specification 3, we allow the controls, the group level controls here. So all in all, we find that positive impact is coming from the cost and the value treatments, and the magnitudes of those two are very similar for the group effort. However, for the group size treatments, we don't find any significant impact with specification 3. We do have 2 more sessions to complete, so those results are still preliminary, but we see that we notice that the sign here is not according to theory. It's totally opposite to what theory predicts, just with the group size treatments. So we find that, whenever there's this cost or value advantage, incomplete information does increase group level effort, but it has no impact when the source is group size. With hypothesis 2, we are testing those same information effects, but for our even contests. So across all 3 sources, this is where teams are on equal footing. And we find across all these models, we find that there is no significant impact apart from the value, a marginal positive impact with the value treatments, but the sign is not according to theory. We don't find any significant impact when we average across all these sources. With hypothesis 3, like I said, with proposition 3, what we were focusing on was, regardless of the contest type, what happens to the expected contest level effort. That's where we use the same specification, but we just throw in the data for all the uneven and even contests. And basically what we find is very similar to our result 1. That incomplete information weakly increases the efforts in cost and value treatments, but we don't find any effect for the group size treatments. So this is coming from the uneven contest, because those results sort of take over when we throw in all the data for uneven and even contests. So it pretty much matches the first hypothesis. Hypothesis 4 here is a little bit unique as compared to the prior literature because there are no such papers that test multiple sources together. I think this is where we can compare these three sources of advantage, and we do so just by using those same specifications. We test whether group effort varies according to the source or not. So we do so for uneven and even contests. Basically, we can just go back to that table 1. And like I said, the magnitudes are similar for cost and value. Individual t-tests confirm this finding, but there are differences that arise with the group size comparisons. So basically, what we find here is that group level effort is similar, and the impact of information is similar when the source is cost or value, but there are differences that arise with group size treatments. Lastly, hypothesis 5 is something that has been tested in the prior literature. We're just comparing group effort for advantage and disadvantage groups. The thing that our study adds here is we test this across all three sources of advantage and information conditions, and we find that group level effort is higher regardless of these conditions. So basically, we're using a very similar kind of specification, but instead of information, here we use an advantage indicator. So again, advantage is equal to 1 when groups have either a cost value or a group size advantage. So what we are doing here is we are allowing these effects to differ, these means to differ for advantaged and disadvantaged groups. Basically, what we find is if you look at the bottom 3 or the interaction terms and the coefficients, we find that there are significant differences, or the effort is higher for these advantage groups across all 3 sources and both the information conditions. But the more interesting finding here is that even though this analysis is at the group level, we find that the means for the group size treatment are much more higher as compared to the cost and value. So this is some evidence against that group size paradox. Even though there's a lot of free riding with the group size treatments, we do find that these advantage groups, they really have higher means. That's opposite to really what the theory suggests. So let's move on. We do focus on other outcomes also, but just in the interest of time, let me move on to our discussion. We find a significant evidence of group size advantage, both with our cooperative model and in our empirical results, which also matches the prior literature with lab experiments. But like I said, the more interesting finding is that being in a larger group is actually empirically a more significant advantage as compared to any other source. So our within group cooperation does explain over expenditure to a certain extent. It does account for the fact that, there is this within group altruism between players. And it does also account for a significant group size advantage in theory. Our results do have some important implications for the contest designer's perspective. When we analyze another outcome, that is the probability of winning, we find that probability of winning is so probability of winning does not change much when incomplete information increases efforts. So basically, those competing teams are just increasing efforts pretty like in the sense that their probability of winning does not change. So all these increases are wasteful. So it seems like when the goal is to minimize free riding, incomplete information can help us get there. Now, some of the results are not according to theory, so we do provide some behavioral explanations for that. With even contest, what we believe is going on is that sometimes subjective belief formation may be such that subjective beliefs by individuals, especially in the disadvantaged groups, may or may not be same as the true objective probabilities. Because of that, sometimes it can counteract the effects of incomplete information. And with the group size treatments, basically we find free riding is much more higher, even though we find a empirical advantage over cost and value. Because under complete information, what's happening is that we know when our team is likely to win, but it is difficult to identify free riders because of the stranger's design. So sometimes non-free riders may have this, this incentive to overcompensate. these incentives are diminished under incomplete information. So it's possible that the disadvantaged groups in the group size treatments are not are not sort of increasing their efforts, and it's possible then that's the reason we don't find these information effects. So all in all, our model does explain certain things, but I think it does warrant further investigation of this within group altruism framework. Okay, thank you. Are there any questions?
Well, thank you so much. If anyone has questions, they can unmute themselves or they can type their questions in the chat rooms and I could help and ask the questions.
Yes, I'll make maybe a comment as in sort of a question form. So I like the idea of formulating this cooperative Nash equilibrium, especially in light of so much experimental evidence on people cooperating in public games absent any competition with another group. And now when you place people in a setting where they're now in competition with another group, albeit maybe there's some advantage or disadvantage, it's not that surprising that they don't fall subject to the complete free riding hypothesis. But is there another model that you considered, or you could derive some predictions with sort of a more standard social preferences or other regarding preferences model? Would it lead to the same predictions, or would it be a better fit? I mean, this one is kind of a varies with the size of the group as well. So I feel much higher utility when I'm in a large group, when maybe I don't necessarily feel that more strongly about others. It's just that I feel more confident that our group is going to win because we're a stronger group in the sense of being a larger group size.
Yeah, I think we did consider like other regarding preferences, but there's no standard model in contest theory that we came across. But I think because this cooperative model kind of accounts that at least for one team. But I know that there's this other model out there. It's called parochial altruism. I think we read about that in Sherry Mehta's review, which says that actually it could be that you care about your team members, but you also have some enmity against the other team. So maybe that could be something to look at, but we haven't really found a model in contest theory that does that systematically.
Sure.
So I think you're right that there's this competition also here. So maybe that makes more sense. So that's one of the extensions that we think, just to account the fact that maybe people don't like their team, their competing team winning. So something like that.
Yeah, you could. I mean, there's somebody else who could speak more about this here, but group identity is another important factor. Right.
Yeah, that's true. Okay, yeah, that's nice. Thank you. Okay. Any other questions, comments?
Cool. We don't have much time left, so thank you again, Ambassador, for the
presentation. Thank you so much.
Yeah, our next speaker is Christopher Brown from Purdue University, and he will be presenting on contest with network externalities.
All right. Yeah, so thanks everyone for being here. So yeah, I'm going to present this work with Luke Busey at Florida State on contests with network externalities. So we all know, I mean, presumably the contests are used to model competitive environments where participants expend resources in the attempt to secure some prize. But the standard contest model assumes players who do not win are indifferent about the identity of the winner. But we could think about some examples of settings in which agents may have more general preferences over the allocation of the prize. So there's some related literature that talks about identity-dependent externalities, where the prize may generate some externalities that impact players other than the winner. And specifically here, we're going to look at how this works through an underlying network of connections. And our main question is how the presence of these externalities affects behavior in imperfectly discriminating contests. So we're going to look at Tulloch lottery contests. And the reason for the emphasis on imperfectly discriminating here is that there's, as I mentioned, some work on identity-dependent externalities, but it's been primarily limited to these perfectly discriminating settings, all pay and winner pay auctions. So let me start with a couple of examples to motivate kind of the setting here. So our first example, we can think about several communities lobbying a city planning commission that's deciding on the location of a new public playground. And if we assume that the ideal location for each community is in their own neighborhood, but beyond that, if it's not placed there, they would prefer the playground be located in a closer neighborhood than a more distant one so that they still have some access to it. So in this case, the underlying network is a spatial network which connects the different communities, and it should affect the lobbying activities of these different communities. In general, we might expect the presence of positive externalities to increase individuals' incentives to free ride off their neighbors' investments, because now I don't have to necessarily win the contest if my neighbor, if the next community over does. In a second example, consider professional sports teams pursuing a top free agent athlete. They'll be negatively affected if the athlete signs with a divisional rival, much more than if the athlete signs with a team from a different division, so a team they'd compete with less intensely. So for example, in Major League Baseball, the Red Sox would much prefer that a superstar free agent sign with the Padres than with the New York Yankees, who are their major rival. So in this case, our network is capturing the degree of rivalry between the competing parties. And we have a negative externality, which we might expect to intensify competition compared to the standard setting. So turning to, I'm going to just provide a quick overview of what we do in this paper. So we developed this stylized theoretical framework that's extending the standard contest model to allow for these network externalities. And specifically, we do this by allowing the allocation of the prize to generate an externality in the winner's neighborhood. So by neighborhood, I mean the other individuals connected to the winner. And then we're going to look at the impact of the network structure on investment behavior in contests with either positive or negative externalities. And what we find is that there's a unique equilibrium for negative and sufficiently small positive externalities, but for sufficiently high positive externalities, multiple equilibria may arise. And in general, as I mentioned before, positive externalities are going to tend to induce free riding incentives and reduce competition, while negative externalities will stimulate more aggressive investment behavior in the contest. A lot of our focus is on two broad classes of tractable network structures, and I'll define these momentarily, but we're going to look at regular and core periphery networks primarily. And then we design an experiment to test some of the predictions of the model and look at some behavioral motivations of observed patterns of investment. And just to provide an overview of this, we designed the experiment to look at contests between 6 agents connected by a network structure and impose an externality on non-winners that are connected to the winner of the contest. We examined 4 different network structures that are varied between sessions, and then 3 different values of externality that we're going to vary within the session. In general, what we find is that there seems to be robust support for the comparative statics predicted by the model. We do find overinvestment on average, which is pretty standard of experimental contests at this point, but there is considerable heterogeneity there. And some behavior that seems to be consistent with the influence of some social preferences or efficiency concerns. So really quickly on related literature, as I mentioned, there's this existing strand of literature on identity-dependent externalities in winner pay auctions. But we have this imperfectly discriminating setting that's more in line with, probably most closely in line with this work by Linster. But our work is a bit more general than that. And then it's also pretty closely tied to the literature on games played on networks, specifically this Bernoulli et al. 2014 paper, which shows that equilibria are, in the setting they examine, are related in some way to different characteristics of the network structure. And we find some similar results that I may not have time to get into given the time constraints. Okay, so jumping into the model. So briefly, just to kind of recap the standard contest model, and then I'll show where ours diverges from this. So we have some set of individuals that are simultaneously choosing investments in the contest. And the probability that some player I wins the contest is given by this Tullock contest success function. And in the standard setting, the winner receives a prize, some fixed prize with value V. And this standard contest has a unique symmetric Nash equilibrium given here by X star. So we're going to modify this setting slightly by introducing this network. So agents are now arranged in a network, which we represent by an adjacency matrix G. So we focus on undirected symmetric networks. So Gij equals Gji equals 1 if I and J are linked and 0 otherwise. And so in the contest, the allocation of the prize to some player I is going to impose an externality on each agent J who is connected to I. So anyone in their neighborhood in the network. We're going to focus on symmetric proportional externalities. So proportional to the prize or the value of the prize, so alpha V. And at this point, we're going to fix V equal to 1 just for simplicity in the theory. In the experiment, it's set to 500 tokens. And so our expected payoffs in this setting look like this. So this PI minus XI is the standard expected payoffs in the contest, and we have this additional externality term. So alpha is our externality, and then we're looking at the total probability that I'm hit by the externality if one of my neighbors wins the contest. So the best responses here, so we can rule out investment profiles with less than 2 active agents as being part of an equilibrium. And so this allows us to write expected payoffs as shown here, where we can just use this interior part of the contest success function. And then we can note that the payoff functions are strictly concave, so we have a unique best response given as shown below. And this is aligned pretty closely with the best response functions for the standard contest with, again, this additional term resulting from the externalities that we've introduced. So this slide tells us the full set, full characterization of the set of Nash equilibria. So for any profile of investments, we denote by A, the set of active agents, so those choosing positive levels of investment, and N minus A, the inactive agents. And we can classify all Nash equilibria as satisfying these first order conditions, one for each active and inactive agents. So I want to talk about a couple specific types of equilibria. So when alpha equals 0, the best response functions are the same as those of the standard contest because the externalities don't affect play. But in general, when alpha is not equal to 0, and as long as we're not in this complete network where everyone's connected, we may have equilibria in which some agents are inactive and choose to invest 0. And so we call these specialized equilibria following the work of Bernoulli and Cranton. In a specialized equilibrium in our setting, the set A, so the set of active players, is a maximal independent set, so no active players are linked. And each inactive player is going to be linked to at least 2 active players. And because no active players are linked, they can't affect each other through this externality channel. And so we're going to have symmetric equilibrium investment levels among the active players. And so just to provide a quick example, if we consider the 6-player circle where each person's connected to their 2 immediate neighbors, there's 2 specialized equilibria that can arise when alpha becomes sufficiently high, where every other player is inactive, and then the other players are active in choosing this standard contest investment level among 3 people. Okay, so getting into our specific classes of networks, first one we look at is regular networks. So for any network, we can define the degree of a player as DI, which just tells us the number of other players they're connected to. And then a regular network is one in which every individual has the same number of neighbors. And we find this result that in regular networks, there's a symmetric pure strategy Nash equilibrium where everyone plays this value X star. And just to point out a few things here, we can see that this is has some similarities to the standard contest equilibrium. We have this n-1 over n squared. And the only difference here is this additional alpha k term. And some important comparative statics here are that with negative externalities, this will be increased above the standard contest equilibrium. And with positive externalities, will decrease investment levels in free ride. And these effects are amplified depending on the magnitude of K. So as the network becomes more connected, these effects become stronger. And so a couple of examples. So going back to our circle, we can see this symmetric equilibrium where everyone has 2 neighbors. So we have a 2 alpha. And then similarly in the complete network, everyone has 5 neighbors. So the change here is in this, this multiplier on alpha. Okay, so then onto our second set of networks, core periphery. So core periphery network's pretty broad class, but the main takeaway is that there's a set of highly connected core players and a set of less connected periphery players. And so I'm going to skip over this a bit for the sake of time, but we restrict the set a little bit, imposing some structure, but it's still a lot. We can still study some pretty commonly examined structures. So let me just go to a couple of examples. So a pretty popular one is the star network, where we have a single core player and then a set of peripheral players that are all connected to that core player. So the second one we're going to look at in the experiment, we call the CP2 network, where now we have 2 core players connected to each other and each connected to 2 peripheral players. In both cases, the peripheral players are always connected only to a single core player. So what we'll find in this class of networks is that we get a semi-symmetric equilibrium where players of the same type will choose the same investment levels, but it may differ across types. So our first example, looking at the star here, we can see, so I'm just going to focus on this graph. We can see that for negative values of alpha, star, the core player invests very highly because they're very structurally exposed to the externality. But once the externality becomes sufficiently positive, they find it worthwhile to just drop out of the contest and free ride, because regardless of who wins the prize among the peripheral players, they'll get the externality. And once they drop out, we now have this standard contest among the peripheral players. And then we find a similar result among in the CP2 network, but these core players are less structurally exposed, so this effect isn't as strong, but they still similarly eventually drop out. Okay, so I'm going to jump ahead. I think I'm going to skip over this for the sake of time and get to the experiment. Okay, so in the experiment, we're looking at groups of size 6, each player given an endowment of 800 tokens and competing for a prize worth 500. Like I said, we'll look at 3 different externalities, so a high negative, a 0 baseline condition, and a high positive. And so if an individual wins, they get 1,300 minus their investment. If they lose and they're not connected to the winner, they just lose their investment. But if they lose and are connected to the winner, they lose their investment and they're affected by the externality. And we're going to look at these 4 network structures, which I've already introduced. So our complete and circle are our regular networks, and our star and CP2 are our core periphery networks that we're going to look at. So we vary the network between sessions and the externality within session. So for each network, we're going to vary the externality across 4 different blocks and play multiple rounds. So we always start with a baseline alpha equals 0 condition for 10 rounds. And then in blocks 2, 3, and 4, we'll run positive and negative values of the externality and a second baseline condition. And so the baseline always has 10 rounds, positive, negative is always 15. And we vary the order of the externality here to control for any order effects that may arise. Quickly on the procedures. So random assignment to fixed groups of 6. Importantly, we only reveal the next externality value in the next block after the previous block was completed, so they have no idea what the next value will be. And we pay subjects 1 randomly selected round from each block. All right. So this is what the data looks like. We run each order for the complete and circle, and for the star and CP2, we ran some additional sessions because we had, there's less data on the core players. So in the case of the star, there's only 1. So we ran a couple of additional sessions for more observations there. So these are what the theoretical predictions are for each network and externality treatment condition. And so what we should see here, for the complete network, we should see investment levels decreasing as the externality increases. In the circle, we do have multiple equilibria in this positive externality case. So in the symmetric case, we would expect to see, again, decreasing externalities. But we're going to look into more of this specialized equilibria if this occurs. There are 2 different ones, so there's a potential coordination problem here. But we'll see if that occurs. For the core periphery networks, in both cases, what we should expect is that for the core players, their investments decreasing and then they eventually drop out in the positive case. In the peripheral players, their investment levels we shouldn't expect them to be too different across treatment conditions necessarily. But we'll look for this standard contest level in the positive case. All right, so to the results. So the first thing just quickly is that looking at the block 1 baseline comparison, we wanted to see if there was like a placebo effect of just the network structure. We don't see any differences, significant differences here. So any results that follow, we interpret as being arising from the externality rather than just the presence of a network. So looking at the regular networks, we find pretty strong support for the comparative statics. So in the complete network, average investments are decreasing, strictly decreasing in the value of the externality. In the circle, the only exception here is that we don't find significant difference between baseline and positive. And again, this may be some indication that there's a miscoordination in some players who shouldn't be active in a specialized equilibrium are, and it's driving that up a bit. We're going to look into that a bit more. And again, we find pretty consistent overinvestment. Yes, let me move on. I'm running a bit short on time. In the star network, we find that the comparative statics for core players are supported. They are strictly decreasing the value of the externality. But importantly, we don't see average overinvestment in the negative case, and they don't drop out in the positive case. And then the other point here I want to mention is that among the periphery players, we see declining overinvestment rates. So in the negative case, they're overinvesting a lot. And the positive case, not so much. And we take this as maybe evidence that there's some social preferences here. So core players, for example, may stay in the positive case because it's going to benefit everyone in the event that they win. I think I'm about out of time, but I'll just say that there's a pretty similar story in the CP2 as the STAR. We see a lot of the same trends here, and I'll wrap up really quickly. So on the theory side, we model these contests between agents connected on a network, where the prize is generating some identity-dependent externalities. And we see that positive externalities tend to induce free riding, while negative externalities stimulate more aggressive investment. And in the lab, we see mostly robust support for our comparative statics predictions. There's, again, mean overinvestment in pretty much all treatment conditions. And we see some evidence of maybe behavior that's in line with social preferences or some kind of efficiency concerns. Okay, and I'll stop there. Thank you, and I'd love any questions or comments you may have.
I have a quick question.
Yes.
So for the fact that the extent of overinvestment depends on your network position. So if you calibrate a very simple social preference model, let's say just altruism over the people you're connected with, would it come out that the more connected you are, the more you would overinvest? So is there, I'm just wondering whether that directional prediction would be true.
So if I understand the question right, I would think it would depend on the value of the externality. So
okay.
If you're more connected in a negative case, that might dampen your overinvestment because now I'm going to harm everyone if I win.
I see. Right.
In
right
positive
right.
case,
Yeah.
I should see higher overinvestment.
Yeah. Okay. Nice. Thank you.
Okay, any other questions? If no, thank you so much, Christopher, for the presentation. So our next speaker is Professor Yan Chen from the University of Michigan. She's going to present virtual teams for the modern workplace.
Thank you. Okay, so thanks everyone. So this is joint work with two of our doctoral students, Teng Ye and Wei Ai, and my computer scientist colleague Qiaojun Mei, and our DD collaborator Jieping Ye, who's also a data mining researcher. So I'm going to first talk about the gig economy. So this is a field experiment conducted on the DD platform, which is a ride-sharing platform. So for workers in traditional sectors, including college professors, we derive part of our identity from our work, and we develop bonds with our coworkers who tend to be fairly stable. And there is a clear career trajectory. So if we perform well, you get tenured and then you get promoted to full and so on. For gig workers, including people at ride-sharing platforms, they have a lot of autonomy and flexibility, but there is a perceived lack of work identity and bonds with coworkers. And so these are from sociologists' work who rely on interviews. For instance, one of the gig worker for TaskRabbit said, talking about his job, every day he gets up, the algorithm assigns him some tasks and he goes and do it, and next day it's the same. So he says that, these are jobs that don't lead to anything. And a DD driver also say that I have no interaction or relationship with other colleagues. And so just to compare our platform with something that people are more familiar with in North America. So Uber has about 4 million drivers and 14 million rides per day. Lyft has 1.4, and DD has 21 million drivers. So it's size-wise, it's a lot larger than Uber and Lyft combined. Okay, so we're going to propose an identity-based solution. So Luke mentioned this before, when commenting on Vasuda's paper. So the idea is to create drivers' organizational team identity and increase their engagement and productivity. The theory that we rely on, which I'm not going to talk about, is social identity theory from psychology and also identity economics from economics. And so this is a contest session. So we also rely on group contest theory. We also have an abundance of lab experiments and field experiments. And I will do some shameless advertisement for a new survey paper on identity groups and teams that just came out in August. So we did 2 experiments on DD. The first one is a short-term team contest that I won't have time to present. I'm going to present the second one, which is called status contest, that basically constructs a leaderboard for the drivers. There's also a growing literature on the ride-sharing economy, not surprisingly because the chief economists at Uber and Lyft are both into field experiments. So I'm going to dive into our experiment design. So the experiment was conducted towards the end of 2018, so that's about 2 years ago. For the first stage, we form teams and give them some team building exercise on the DD platform. And then everybody participates in a short-term inter-team competition experiment, and that was incentivized. So the short-term contest was built on our first field experiment. After the first field experiment, they built in some of the algorithms that performed well in that experiment into their platform. So this is like the contest that they're familiar with. Once the contest is over, we start our intervention, which is what's called stage 3, long-term competition. It's actually only 3 weeks. And so we wanted to run it for much longer, but was not successful in negotiating with the platform. So in the long term, in this, what we call the status contest, there's no monetary incentive. So drivers form teams of 7 in stage 1. And if you're in treatment 1, on your app, which I'm going to show a mock-up, you basically have a team leaderboard, which shows that the teams that you were matched with in stage 2, just basically at the end of each day, how much each team performed in terms of revenue. There's also a within team individual leaderboard. So within your team, you see how much everybody else, everyone makes in decreasing order. In treatment 2, you only see the within team or individual leaderboard. So then the control condition is you're back on your own. So you're an individual driver. You don't see the team structure at all. So once this is over, so this went on for 3 weeks, we run an evaluation, basically another 1-week contest with bonus, and see whether the team effect persists. And then there was a survey. I want to also say that to look at the effect of identity building on retention, we obtained data from DD 3 months after the contest and see whether there is an effect on retention. It turns out that the answer is positive. So the 3 cities we selected are quite different in terms of size and geographic location. So it's Beijing, Taiyuan, and Kunming. One thing that I want to point out is, which will matter when we see the results, is before we started our experiment, 90% of the orders from customers were fulfilled in Beijing and Taiyuan, which means there's a 10% gap. And in Kunming, 98% of the orders were fulfilled. So what is the implication of, so why was there a 10% gap? The story was that Didi was competing with Uber China for a while, and because of the competition, they basically had a Bertrand competition. Because of the competition, the price was really low, and then Uber pulled out of China, and Didi effectively became a monopolist in most Chinese cities. At that point, they decided to also implement search pricing, but customers remember how low the price was, so they got huge basically complaints on social media, so they backed down and took away search pricing. In its place, they implemented a queuing mechanism. So you might open up your app and order a car, and it says, you know, you are number 37 on the waiting list. You you have to wait for 45 minutes. By that time, you basically decide you might just take alternative transportation. And so in the larger cities, there is this 10% gap, largely from the queuing mechanism. So these cities are quite different. And when we started the team formation stage, we emailed all eligible drivers, registered drivers in these 3 cities, and randomized them into these 3 different treatments. So each treatment had about 9,000 drivers. Drivers can volunteer to be team captains, and each captain can organize a team of 7. So some of these, like including the parameters, were all remnants from our first field experiment, which turns out that reduces our flexibility in the subsequent field experiments. Okay. So the contest mechanism for the short-term team contest is the best of 5. And each winning team gets 1,000 yuan RMB in Beijing. So these are calibrated based on their salary, their regular earnings before the contest. So the performance, the total revenue is calculated by just counting the top 6 drivers in a 7-driver team. So it allows some people to, take a break. This is what the leaderboard looks like. So this is a mock-up. So if you're in the team leaderboard treatment, you see the team ranking, right? So of the 5 teams that were grouped together. In the individual leaderboard, you can further look at the individual leaderboard, everybody's ranking at the end of the day. If you're in the individual leaderboard treatment, you only see the driver ranking in your team and how much they earned. So these are the 3 experimental conditions, and then we implemented a surprise short-term contest, the post-experiment survey. So let me go through the hypotheses. These are pre-registered. So the first one talks about the average treatment effect. So drivers receiving team and individual rankings are more productive than those receiving individual ranking alone, who in turn are more productive than those in the control condition. And we anticipate that this same thing holds in the surprise contest and retention. Hypothesis 4 is not really a treatment effect. It basically says that more productive and experienced drivers are more likely to volunteer to be team captains. So what are these hypotheses based on? It's primarily by putting group contingent social preferences into the team contest, the status contest model. Okay. So let me look at the results. So we have data 2 weeks before we started, we announced our contest. So all the analysis are panel analysis using difference in differences. And so the pre-experiment condition will be the 2 weeks pre. Okay. So the first one is, basically looking at the average treatment effect or testing hypothesis 1. We had anticipated that team leaderboard would generate the highest effect, followed by individual leaderboard, and followed by the control condition. So the control condition is the omitted variable. The direction overall does not follow what we anticipated, primarily because Beijing has the largest number of drivers, and in Beijing, the individual leaderboard actually works better. And the other part is, if you remember the hypotheses, we did not anticipate, when we pre-register our hypothesis, we did not anticipate heterogeneous treatment effects by location. So it turns out that Beijing and Taiyuan, the drivers behave very differently, and nothing is ever significant in Kunming. So I'm not going to talk about Kunming from now on. And remember, before we started the field experiment, 98% of the orders were fulfilled. Basically, it was in equilibrium before. So in Beijing, the most effective contest was the individual leaderboard. So it's the within team individual comparison, and in Taiyuan it was the team leaderboard. So Taiyuan is like our textbook case. So the team leaderboard did better than individual leaderboard, which did better than the control condition. What are the numbers in square brackets? These are false discovery rate adjusted Q values to correct for multiple testing. And we adopt the same convention of 5% for p-values and 10% for q-values for cutoff. Okay, so that's the first hypothesis, not exactly according to what we anticipated, except in Taiyuan. So the short term after contest, so if you look at any spillovers after the treatment is over, it turns out that the team leaderboard did better than the control condition, and the effect size is about 3% compared to the control group's income. And again, in Taiyuan, team leaderboard, if you compare these two coefficients, it does better. So we explored the reason for why Beijing and Taiyuan are so different. One difference is we happen to have every driver's hometown location. So we computed their hometown distance from the contest city. It turns out that people in Beijing, the average distance within a team is about 300 kilometers, whereas in Taiyuan it's 100 kilometers. So which means most of the drivers in Taiyuan are local, whereas in Beijing, they're from all over the place. And this is consistent with, excuse me, the gig worker population, the composition of gig workers. Okay, so here are just the figures. So this is in Taiyuan. So here you have the team leaderboard condition. And the blue bar in the middle, this is the 3-week intervention, and this is the week afterwards. We normalize the start of the contest to 0. And the dotted line here is the control condition. And so here's when the contest is over. And what you continue to see is this peak is the end of the fiscal year, which is the end of December. There are lots of prizes and other activities. So you see this general peak, and this is going into Chinese New Year when people are going home. So here you see a clear separation of the effect of team leaderboard. In Beijing, you actually see the opposite, although the effect size is not as large. So it's the individual treatment, individual leaderboard that seems to work, that works better. This is Kunming. So the nothing is significant in Kunming. What about retention? So one of the reasons for building work identity, that how we convinced Didi to run this experiment is because of the high turnover rate, and that's not only a problem for Didi but also for Uber and Lyft. So here, 1 week after the experiment, if you look at the team leaderboard, you have, workers work significantly longer. This is 11% of a workday, and the workday is 10 hours long. So the algorithm will just lock them out automatically if they work exceed 10 hours. And what you see is across all 3 cities, it's about, they work 1 extra hour per week. Which is fairly large, considering that lots of these workers are part-time. And in Taiyuan, it's about 4 hours per week, 4 extra hours per week. So that's 1 week afterwards. This is 1 week before Chunyun, which is about 7 weeks after. Okay, and the effect is fairly stable. We also, I don't have the table here, but we have the 3 months after, and the effect again is stable, which is the 3 month after result is remarkable because lots of these drivers are migrant workers. So during the Chinese New Year, they go home, and there they can make a decision of whether to come back or not. And the fact that you see that team leaderboard continue to have that effect is after the Chinese New Year is quite remarkable. So the fourth result is to test our hypotheses about who wants to lead, and more productive drivers and people who have served as captains before are more likely to lead. Also, more experienced drivers measured by their DD age. We had some survey results, and the survey response rate is not great, only 15%. And lots of people who responded say they like the survey, and citing team belonging and making friends, so identity and bonds, essentially. So let me wrap up. So what we find is that team contests increase driver productivity. And the 2 types of leaderboard, the 2 types of status comparison are different in different cities, have different effects. I think what's really one nice result is that the team leaderboard had significant overall effect on retention across platforms up to 3 months afterwards. And we actually don't have data for more than 3 months. So yeah, so this is all. Any questions? All right.
Okay, I have a question. Sorry.
Yeah.
Do you have any data about the social interactions happening between the team members in the cities? Like, could you?
Yeah. So we. The short answer is no, except for survey data. So we have evidence of survey data. What Didi did was they did an interview. They interviewed with 20 drivers, but that's a very small sample, and lots of them mentioned, finding friends, especially because the 2 algorithms that performed really well in experiment one is hometown similarity, the other one is age similarity. And these 2 algorithms were put into production, so they use it in their so 60% of the teams use these two algorithms. So because a large fraction of the drivers were migrant workers from other provinces, especially in Beijing, they said that the contest helped them find friends from their hometown, for instance, and they talk about making friends, and we don't have the communication data.
Oh yeah. But do you have any survey data asking about like their well-being? Because like one of your motivation is saying that people are pretty lonely for like these gig workers.
Yeah. So they do, of those who responded, people talk about liking the contest. Xizhi Lim?
Yes. Hi, how are you? I have a question.
Yeah.
So do you mind sharing why did the platform not let you continue the stage 3 experiment? Because I thought if you could do it longer, then maybe the team leaderboard effect could come out, right? If people are just, not coming from the same place, but they could build relationship over time, and then now they actually perform as a team and so on.
Yeah, so when we negotiated, we said, you've been running these short-term week-long contests, and that's not really taking advantage of the identity that results, and they
Right.
said, how long is long-term? So we said a year, and they basically, at the time Didi was only 5 years old, so that seemed like very long. So in the end, the negotiation result was 3 weeks. But I want to say that now it is part of their infrastructure. So every city built long-term teams.
I see.
Yeah.
Thank you.
Yeah. Thank you.
Cool. Okay, then it's my turn right now.
Yeah.
Okay, thank you guys for sticking around. So I'm Eileen Zhao, a PhD student from UCLA Anderson School of Management. So I'm happy to present this work, The Cooperative Consequences of Contests. So this is a joint work with Professor Jamie Lian from Chinese University of Hong Kong and Professor Jie Zheng from Tsinghua University. So many theoretical papers has shown that contest has an advantage to motivate individuals under limited resources. And hence, contests are really prevalent in many real-world consequential settings, such as job promotion in the workplace, project biddings, as well as academic competitions. And typically, these contest incentives differ under different settings. For example, in the bidding contest, a single prize will be awarded to the winner only. However, in other workplace settings, a total revenue will be shared among the same team members based on individual performances. Importantly, in competitive societies with limited resources, contests are becoming increasingly important because people have to compete in repeated competition in order to distinguish themselves from the other peers. However, exposure from competitive environment and these experiences in participating in contests could have some unintended negative consequences in other domains beyond contests. For example, the competitive mentality that helps a person to do well in the contest may be really difficult to turn off in settings that require cooperation. Second, contest outcomes often involve some unequal distribution of resources, and which may generate some negative emotional impacts on subjects and affect subjects' subsequent behavior. More importantly, we think our implication is especially relevant in a competitive societies because this repeated participation in contests could have a longer run consequences in shaping people's social preferences and thus their behaviors. So in these studies, we asked 2 questions. The first question is, how does participation in contests can shape people's social behavior in a more general settings beyond contests when one's self-interest and the social surplus are opposing forces? And second, what are the relative impacts of different contest formats on social behavior? So specifically, we want to examine like winner-takes-all contests, including standard all-pay auction contests, as well as probabilistic color contests, as well as proportional prize contests. Finally, with piece rate with social comparison as our baseline. So we conduct a real effort lab experiment to examine these two questions. So our research is related to several strands of literature. So there are a strand of literature that document these negative behaviors generated during the contest. For example, there will be reduced cooperation and increased sabotage, which could be actually counterproductive. Second, our paper also adds to an emerging literature that studies the spillover effect of contest incentives relative to other incentives like team-based incentives. Also relatedly, our paper is also related to studies that document the negative outcomes due to social comparisons as well as pay inequality. More broadly, our paper is related to studies that investigate how economic incentives influence social preferences. So different from these existing studies, our studies also focus on testing the relative impacts of contest incentives. And to our knowledge, this is new to the literature. Okay, so here is the experimental design. So there are in total 3 stages, and in each game, subject will be randomly paired with a different partner in each game. So in our first stage, we will measure the baseline prosociality of subjects using prisoner's dilemma, public goods game, and trust game. In our second stage, subjects will compete in a real effort contest with a different partner and do a real effort task. So their task is to count the number of ones in a series of 7x7 matrices with randomly ordered 0 and 1s. So subject's goal is to correctly count as many matrices as possible within 6 minutes. And after the contest, the performance feedback will be shown to both subjects, including both players' performance and their payoff. And in the third stage, the subjects will repeat the same social games, again with a different set of random players. After that, they will complete the exit surveys and receive the experimental payment. And importantly, in this experiment, subjects will not know against coming next in order to avoid this bad reinduction behavior. And they also will not receive any feedback until the experiment is over. So the only exception here is the contest result. So this is the payoff table for the 3 social games and as well as for the contest treatments. So here we adopt these 3 social games in order to assess different aspects of prosocialities more comprehensively. So for example, in order to measure like subjects' willingness to coordinate or cooperate with other people, we mainly use prisoner's dilemma and public goods game. And we also use trust game to measure people's trust towards other people. In public goods game and in trust games, both subjects will have like 10 endowments so that they can choose any integers between 0 and 10 to contribute to the public goods or to send to the other player. And regarding the real effort task, across subjects, we introduce 4 treatments in order to make the commonly used contest incentives in real world settings. So our baseline is piece rate, in which subjects will earn 2 points for each correctly counted matrix. And our second treatment is proportional price contest. In this contest, a total of 150 points will be shared between subjects in proportion to their relative performance. Our third treatment here is all-pay auction contest. And in this contest, only the winner can get a total of 150 points, and the winner is whoever who has the higher correct counts. And our final treatment, the talent contest, is also a winner-takes-all contest. However, here the winner is determined probabilistically in proportion to their relative performance. Okay, in order to compare the relative treatment effects, we begin with the benchmark hypothesis called effort correspondence. So the idea of this effort correspondence hypothesis is that a competition where the compensation is potentially less directly proportional to expected effort in the contest will lead to a larger drop in prosociality. So the idea is that the efforts that goes unrewarded may trigger more negative reactions by subjects and lead to larger decline in prosociality. So we rank the 4 treatments from the least effort proportional to most, and the order is all-pay auction contest / talent contest, followed by proportional price contest and piece rate. So the intuition behind this ranking is that there is least correspondence between effort and your payoff in both all-pay auction contests and talent contests, because the equilibrium effort is the highest in the all-pay auction contest, but subjects may still earn nothing from the contest, whereas the equilibrium effort level is a little bit lower in talent compared to all-pay auction. However, those subjects who has a higher correct count than their partners may still earn nothing due to the probabilistic winning structure. In comparisons, in the proportional price contest and piece race, subjects will earn a positive payoff as long as you exert some positive efforts. And moreover, there is the correspondence between effort and payoff is highest in this piece rate. So, however, to our surprise, our experimental data did not support this effort correspondence. And in contrast, rather, it is more supported by an alternative hypothesis, which we will prevail here. So this another potential hypothesis is called chance for fair division. So the idea here is that a competition that has a greater chance for a fair division, while subjects may fail to achieve it, may generate a larger negative reactions and hence leads to greater drops in prosocialities. So these 4 treatments rank from the greatest chance for fair division to least is proportional price contest, followed by piece rate, and then talent, and then all-pay auction contest. So the proportional price contest is a revenue sharing contest, and it offers the most salient cue for a fair division, as both subjects can get a big prize with little efforts if both people coordinate. And this is followed by piece rate. The idea here is like subjects could earn similar payoffs if they perform about equally. And the 3rd and 4th treatment is talent and all-pay auction contest, because these 2 are winner-takes-all contests. However, the expected payoff in talent contest is more fair and less extreme. Okay. So we ran our experiment in December 2017 with a total of 100 subjects. So as you can see that there is large payment variations in the experiment due to our introduction of contest incentives. Okay, so now is the aggregate results. So generally, we find a decrease in prosociality across all treatments, and this is mainly driven by prisoner's dilemma and trust game. For example, the cooperation level in PD declined from like 42% to around 29%. Similarly, the amount sent to the other players to trust game declined by around roughly 20% compared to the baseline. On the other hand, the average contribution in the public goods gains only declined around 40% compared to the baseline, which is smaller and less significant. And finally, we did not find any significant differences in the ratio of money returned to the senders. And part of the reason is that 40% of the receivers received 0 amount from the senders at least once in either round of the trust game. So since we did not use a strategy method to elicit receivers' response, it is pretty difficult to assess the within-person effects for receivers, and hence in our later analysis, we will mostly focus on senders' behaviors in the trust game. Now we will go through each social game to see the relative impact of contests. So this graph plots the mean cooperation level in both rounds of prisoner's dilemma. And this table here summarizes the within-person differences across treatments. So from both the figures and table, we can see that. So the cooperation level in prisoner's dilemma decreased significantly in piece rate, proportional contest, as well as for talent contest. However, like the cooperation level actually increased a little bit in the all-pay auction contest. Our pairwise comparison between these drop in cooperations also reveals that the cooperation drop in the proportional price contest is significantly larger than the drop in all other 3 treatments. And on the other hand, the cooperation drop in all-pay auction contest is significantly smaller than the drop in all other 3 treatments. So based on that, we have our rankings in the prisoner's dilemma as proportional contest larger than piece rate, or slash talog, and finally followed by all pay auction contests. And this is exactly the same rankings as predicted by chance for fair division hypothesis. Okay, for public goods games, so this figure just plots the distribution of public goods contribution in both rounds of the games. So from this figure, we can know that subjects are shifting to lower contribution in the second round of the games, and especially for zero contributions. And this table shows that although on average, the public goods contribution decreased in all treatments, this is only significant in proportional price contests. And our pairwise comparison also only find that this drop in contribution in proportional price contest is only larger than the drop in all pay auction contest, and there is no significant differences in the contribution drop in any of other treatments. So since we only find one significant inequality here, but nevertheless, this inequality is more supportive of chance for fair divisions rather than the effort correspondence hypothesis. Finally, for trust game, these figures again shows that more subjects are increasing zero amount sent to the other players in the second round of the games, and especially in the proportional price contest and in talent contest. And this table shows that for among all these four treatments, the trust declines significantly in both basically all these three contest treatments, but not so in this P3 with social comparisons. And our pairwise comparison of this trust drop also reveals that proportional price contest and talent contest has a significantly larger drop than the drop in the P3. And for the results in the trust game, we find this is actually more in line with effort correspondence hypothesis, because this hypothesis correctly predicts that the least drop in trust is in the P3 treatment. Now we will want to measure the overall change in people's prosociality in order to see whether subjects' behavior change consistently across the three social games. So motivated by the idea that deviations from playing Nash in all three social games contribute to a greater social efficiency, we define our prosociality index as the sum of the percentage gain in social efficiency under subject's actual social behavior relative to the social efficiency under Nash equilibrium behavior across the three social games. And since this social efficiency is determined by both subjects, and subjects do not know the other subject's action when doing their own action decisions, we consider three versions of efficiency games under the assumption that the other player is playing selfishly, playing cooperatively, or randomly. And here we will mainly present the results when other players play selfishly, because this is the most common behavior is observed in the experiment, but the results are qualitatively similar using the other two versions of index. So here, this graph just plots the prosociality before and after the contest. So with the x-axis is the efficiency gain before the contest, and the y-axis is the efficiency gain after the contest. So first, we can observe that there are many dots that are below the 45-degree lines, and especially for the proportional price contest. And moreover, the magnitude of decline in prosociality is larger than the increase in prosociality here. And finally, we still find that there is a substantial fraction of dots that are staying on the 45-degree line, suggesting that people are not changing their overall prosociality. We also compare the relative decline in efficiency gain across treatments. And again, we find that the largest decline is in the proportional price contest, and the least decline is in the all-pay auction contest. And this is the ranking for the drop in efficiency gain, and it is also more consistent with chance for fair division hypothesis. So finally, we decompose our effects between contest winners and contest losers. So one motivation is that contest loser may experience greater negative feelings after contest, and hence they will exhibit more negative behavior after the contest. And in our survey questions, we do find that compared to contest winners, contest losers reported significantly lower emotional states in all of the treatments, especially in these two winner-takes-all contests. However, when we compare like the social behavior change between contest winner and losers, we do not find that contest loser is driving the decrease in prosociality. For example, we only find that compared to contest winners, loser is like decreasing prosocial behavior more in proportional prize contests in Person's Dilemma. However, in the public goods game and in trust games, we find this is actually the contest winner that is contributing more to the decline to prosociality. Okay, to wrap it up, so our studies find increase in Nash equilibrium behavior under contest incentives for all of the treatments, and this is also true for peer-free treatments with performance feedback, and it suggests that social comparison is playing a role here. So an additional control treatment without like performance feedback may help to disentangle this. Also, we find that this rapid magnitude of decline in cooperation games is more consistent with chance for fairness fair division hypothesis, while the decline in trust is more consistent with effort correspondence hypothesis. So one possible interpretation here is that subjects may have this expectation over like the other participations' behaviors during a contest, and these expectations may involve some social preferences concerns like fairness concern or equity concerns. And this foregone chance for fair division may trigger more negative behavior for subjects. However, in a contest that is less effort proportional, it may place greater risk to subjects, and hence subjects may be less willing to take risks to trust other people in later domains. So our findings also have managerial implications for the optimal incentive structures in an organization where both competition and cooperation is needed. It warns against the use of competitive incentives, especially when the incentive is tied to subjects' perception of obtaining fair outcomes. So thank you. This is my presentation. Any questions?
Yeah, I wanted to ask about the lost results slide that you showed, comparing winners and losers.
This one?
Yes, this one. So one possible explanation I would think in the public goods case is, you know, they're playing this public goods game where as a winner, my beliefs about what the loser is going to do may be very important. You know, if you think about conditional cooperative type hypotheses, it could very well be that the winners just expect low cooperation from the losers, and so they reduce their contributions in kind. And then you would see something kind of like this, where the contest winner in the proportional, for instance, maybe expects the so-called loser, who I guess is the person with the lower proportion, right? Might expect them to be bitter, and so they lower their contributions. And I think the same kind of thing could apply maybe well, maybe not so much in the trust game, but it makes it a little trickier, I think, to separate the behavior of the winners and losers here, because I think beliefs are, if you didn't know who was the winner and loser, and it was just kind of strategy method type of elicitation, like if you were the winner, what would you do? Or if you were the loser, it might be easier, but that would be something I was.
Yeah, thank you so much. Yeah, for this point. Yeah, we actually also think of like the role of belief in shaping subjects' behavior, but like unfortunately we didn't ask about these belief questions. So I feel like further conditions where we explicitly ask their belief and also using strategy method as you suggest may be helpful. Yeah, thank you so much. Yeah, Xi Zhi.
Hey, first of all, I thought it was a great idea. I have one quick question. I might have missed it, but are the participants, when they before they play the contest, meaning ex ante, are they identical, or if some of them may have had some advantage? So, for example, if I have a high value for the item in the contest.
Yeah. So our choice of contest is sort of like requires little knowledge, and so we do not expect like the ability differences from the contest participants. However, like because we don't have the observation of the innate ability to count the numbers, so it's just like the assumptions that is lying behind.
Right. I think I was thinking more about, you know, looking at this slide where you do not find this effect about winning or losing experts on social behavior change. I was wondering if you also looked at whether or not if certain subjects, if they had an advantage in the design of the game of a contest itself. So for example, if I were to participate in an auction and you give me a high value, which means naturally I have a higher chance of actually winning the item compared to if you give me a low one, then would that kind of advantage affect social change, social behavior change?
Yeah, I expect it. So like, it seems like people have this sort of fairness concern. So if you give an advantage to other subjects in the contest, I feel like that will generate some negative reactions because it sort of violates people's social preferences concerns. But we didn't sort of examine this in these current experiments, but I think this is also an interesting like further future research.
I see. Thank you.
Thank you so much.
Yeah, I have a quick comment, which is so basically what you're citing is the, you know, there are some essentially behavioral spillovers, right? So if you compare the first block of the public goods game and trust game and so on with the last block, there are two things going on. One is learning. So, you know, one possible control that one can have is just to let them sit there and think about it instead of playing these intermediate contest type games. Or, as you suggested, playing the piece rate without social information. Because with social comparison, it becomes a status contest, right? And so there's learning, and then there's possibly behavioral spillovers from the contest. And there is a small literature on behavioral spillovers which says that the extent of spillover depends on the entropy of the outcome. So for instance, if in and this is very easy to measure. So in the intermediate, the contest type games, you can look at how concentrated or how spread out the outcome is, the empirical distribution is, and that will give you a very precise measure of entropy. So the idea is if the entropy is low, it's easy to learn that behavior. Whereas if the entropy is high, it's harder. So there's, you know, across different types of games, so there has been a fair amount of consistency showing that the amount of spillovers has to do with the entropy of the game. So that could be something that you can look at.
Cool. Yeah, thanks so much for the suggestion. Like, we haven't looked at that before, but we will definitely look at that after. Cool.
Nice.
So, any other more questions? If no, I believe this concludes these sessions, and thank you so much all for participating in this session. And I hope you guys are staying well and enjoying the rest of the conference. So bye.
All right, thanks, and thanks for keeping time.
Yeah, sure.
Yeah, okay. Thanks, everyone. Yeah.
Thanks, everyone.
Yeah.
Bye.
Hi, Luke.